Okay.
So thanks to everybody for being here on a Friday afternoon without air conditioning. So it's really a pleasure to have Morten here with us. So it's an old friend. I think we know each other since more than 25 years already. And probably also people here know him, but just for the people that met him for the first time. So he's a well-known nuclear theoretical physicist in the past. Now he defines himself a computational physicist, but he has a past. So he has a really interesting on the many-body problem, and in particular the nuclear many-body problem and nuclear structure problems. But now it's more interested on computational aspects of quantum networks. And he's going to have been here for almost a month, but we managed in the end. Oh, he's leaving tomorrow, so the last day we managed to give this couple of lectures on generative methods. So I think it's free, so probably people can interact you when they want or make questions. And okay, so, thanks a lot.
It's always a great pleasure to be back, and I hope to be back more often. It's been such a good time, and so we have. So English is the way. Yeah? It's the language. Is that okay? I can speak it with a heavy Italian accent. So if you want, that's the way I. From the north. Listen, I spoke it like this when I went back to Norway. È un casino, tutti i norvegesi. Okay, so it's what I wanted to give you is a kind of description of how you can use generative methods and why these are interesting. And I will try to draw a distinction between discriminative and generative methods. We actually, this morning, we had a discussion with Luigi and Shred here, and we discussed whether we could actually, or one could apply generative methods to unsupervised problems. So I wanted to give you the kind of taxonomy of these different methods. So the most typical classes are supervised and unsupervised. By the way, I guess that many of you are pretty familiar with machine learning. Is somebody who has never studied machine learning here? Okay, so most of the people are pretty familiar. Okay, but I will try to keep this at a level where you can see whether this is useful for you or not. And then hopefully I can demystify some of the mathematics. And many of these models are actually very close to the way things you have seen in, let's say, statistical mechanics. So there is a class of generative methods which are called Boltzmann machines, which have been around for 30, 40, 50 years. But they acquired a lot of popularity back in 2017 for solving quantum mechanical problems. And this was something which was introduced by Giuseppe Carleo, who was at Lausanne and then went to New York and then went back to Lausanne. But he did this PhD in Trieste. And he's been one of the main drivers of using machine learning to solve quantum mechanical problems. But then, you know, machine learning is something you can use for tons of problems. With classification, you can use that to solve differential equations. There's a very hot topic nowadays, which is called physics-informed machine learning. And this is a field where you apply neural networks to solving differential equations. And people who do, let's say, fluid mechanics, when you have a high-dimensional equation, so you have way too many degrees of freedom, you can actually solve complicated differential equations, like in Navier-Stokes equations, using machine learning methods, neural networks. So I will stay a lot, mainly within supervised learning, where you have labeled your data, you know exactly what you're putting in. And then I will also discuss unsupervised learning and why that is also perhaps more interesting for physicists. But both of the cases are actually very interesting. And the type of problems you often end up with are the classification type of problems. So people have used in physics machine learning to classify whether you are below or above a phase transition. So think of running simulations with the easing model. Then you can make images of the distribution of spins. And you know that when you're below a phase transition, then the spins tend to point in one direction, and you have a net magnetic moment. So what you can do then is to make images where you simply produce, let's say, 10,000 images of a situation below the critical temperature, and then you train a model to recognize that, okay, the spins are pointing in a specific direction, you have a finite magnetic moment, and this is a phase or system which is below the critical point. And then you could say this has a label 1. And then you know that when you're above the critical temperature, then the spins point randomly. You can access many more states. And then the net magnetization is 0. So that's a very classical problem in physics, which probably many of you have seen when you study statistical mechanics. The easing model is one of these classical statistical mechanics problems. And then you could train a network to recognize on images which have not been included in the training, to recognize whether this is below or above the phase transition. So this is normally called a discriminative training, because you're giving in the data, you train on the data, and that is able then to discriminate between new cases which you feed in on a trained model. Okay? And then you have the regression type of problems, which I am often much more interested in, because I live in a world of solving differential equations or quantum mechanical Mann-Whitney problems. So I'm often interested in that. And then you also have clustering. And I'm not going to say everything which is on the slides, because you can also most likely read much better than me. And if you look at situation nowadays, typically when we do physics, it's always about finding the relevant degrees of freedom. You want a fast simulation. We often deal with multi-scale problems. There are many people here who've been studying neutron stars. You have an equation of state which defines the microphysics, and then you have typically length scales of 10 to the minus 15 to 10 to the minus 14 meters, and you want to apply that to a neutron star which has a radius of 10 kilometers. So that's a classical multi-scale problem. And you want to use this for physics discovery. You want to use data analysis methods. You want to do uncertainty quantifications. Machine learning theory is actually one of the ways of dealing with this. And I will try to motivate you a little bit more. I'm going to skip this figure. And if you look at, before we move into perhaps the kind of questions and differences between generative and discriminative methods, I just wanted to mention to you some of the methods which you probably have seen many times. So the first box is normally the box for methods which we typically call after the deep learning revolution, roughly 2010. Many of the other methods have been there for decades or even centuries, like linear and logistic regressions were developed back in the 1800s by Gauss and many other people. So linear regression is just a matrix inversion problem. And some of these other methods, like the kernel methods, support vector machines, these are actually examples of you implementing linear algebra methods. But I will have my focus on the first box. But then there's some questions here, because this is a little bit important when you, for the kind of applications you want to do. So a standard machine learning, if you go into a machine learning textbook, if it's not written by a statistician, you will often see an approach which in statistics is called a frequentist approach. So that means you can fit, for instance, a probability distribution based on the data you have. But you're more interested in making predictions and finding correlations. So a standard machine learning case, like if you use linear regression, which I come back to show you the equations, is a case where you fit a function, or you can fit a probability to the data you have. So you train a model. So with that fit, you can then make predictions. So you can say that I now want to use this on data which was not included in the training. And you can find correlations in the data. So one thing which you often do is to set up the correlation matrix. And that tells you, if you're looking at housing prices, you can have one entry, which is the price of the house. The other one is the number of rooms, the number of bathrooms, etc., etc. And you know that the price of the house is often correlated with the number of rooms. So that's a typical thing you will find if you look at the correlation matrix. That would simply tell you that these two quantities, which you intuitively knew are correlated, are actually correlated. So this is predictions and correlations. But then we as physicists, we want to also study the uncertainties, and we also want to look at causation. So what is the probability of A given B? And what are the uncertainties on the parameters we have? And that means often that we want to have a probability distribution. And this leads us to this distinction between roughly discriminative and generative models. So what you often end up with when you're looking at these type of models, you want to have a kind of balance between tractability and flexibility. You want to extract information about correlations to make predictions, you want to quantify uncertainties, and you want to express causalities. And then you also want to represent in a reliable way the effective degrees of freedom. So think of a, is everybody familiar with the partition function? I hope I'm not offending people. You know the partition function, if you take the Ising model again, if you have 100 spins, you have 2 to the power of 100 ways you can organize the spins. There's no way you can calculate the partition function. Okay? So this is about tractability. So you want to deal with problems which you can actually handle in a reasonable way. But then you also want to be flexible. So that means that you want to have a probability distribution which you can adapt to different situations. So this kind of balance between tractability and flexibility is very important. And I will try to elucidate that when we move on. But then I wanted to give you a teaser first. So I'm not going to show much of own results except these 2 slides. So because I promised this act to give more the basic mathematics of discriminative and generative models. And if you're interested, I can send you the slides and the Jupyter notebooks also. So just shoot me an email afterwards. This is a calculation which I actually showed last October when we were celebrating Marcello here. And this is a calculation, a money-body calculation. It's a variational Monte Carlo calculation where the trial wave function is a neural network. Now, the data which you see here, so this is a neural network calculation with a network which has 5 hidden layers and 100 hidden nodes in each layer. And if you look at the figure here, what you have is if you're familiar with many-body physics, so this is neutral matter. This is the energy per particle, and this is the one you see here is what you would get if you run a Hartree-Fock calculation, which is a mean field calculation. Then a standard method in many-body physics is variational Monte Carlo, where you would bake in an ansatz for the wave function, and this wave function has parameters which you optimize so that you get the minimum energy. Essentially, what you're doing here is to integrate a multi-dimensional integral. So you have, in this case, we have 14 particles in a box, which translates into a density. So you have 14 particles in 3 dimensions. So that means that you have the number of degrees of freedom are 3 times 4. And if you want to integrate that in a standard integral, if you have 10 integration points, you would have 10 to the power of 3 times 14 operations you would need to do in order to calculate the integral. You don't do that. You do this stochastically with Monte Carlo methods. That is a variational Monte Carlo calculation. Now, the variational Monte Carlo calculation is often used as an input for diffusion Monte Carlo, which is this DMC. And the one which is variational in this calculation is the one which you see, which is called unconstrained. So that since you can show that the diffusion Monte Carlo calculation, if you simulate long enough, you should approach the lowest lying state, and in principle get the correct energy for that system, that chemical. So in many-body physics, there is a kind of holy method, which is diffusion Monte Carlo, which everybody tries to reproduce in one way or the other. The problem is often that you have so many degrees of freedom that you cannot move to larger systems. And then you end up using different methods. But what we did then, since the variational Monte Carlo calculation is you calculating an integral, and when you calculate that integral with a wave function and you optimize the parameters, you just get a minimum which corresponds to that input. And you won't move beyond that. That's just the variational principle being applied. And in this case, what we did, we replaced this trial wave function with a neural network. And after a given number of iterations, so this is the so-called back propagation algorithm in a neural network, so an optimization step of different steps back and forth. And you actually reach, and this was our big surprise, the diffusion Monte Carlo result. Diffusion Monte Carlo has, it promises to give you the exact energy, but it has a problem when you deal with fermions. And with fermions, the problem you have then is that the way you simulate diffusion Monte Carlo is as a diffusion equation in complex time. So this is why you have to simulate an infinite time, because that's where you recover the Schrödinger equation. And a diffusion Monte Carlo calculation, it gives you the wave function as a distribution of random walkers. And that means that if you have fermions, you know that the wave function can change that. And a distribution doesn't change that. A probability distribution has positive values, always, or larger or equal than 0. So that means that the diffusion Monte Carlo problem needs some tricks in order to attack the problem. There's some people who claim that if you solve the fermion sign problem, there is a party in Sweden at the end of December and beginning of December where you meet the Swedish king and get a prize and so on. Yeah. So it's roughly at that level, right?
May I ask you?
Yeah.
It's not strange if the constraint is below the atom strain.
So the constraint one is actually not variation. That's a problem. So that one is actually not the optimal result. And there's always a discussion whether this diffusion Monte Carlo calculation is correct. So when people tell you that I have now invented new methods, then all alarm clocks start ringing.
I have one question.
Yeah.
So, the neural network, so the back propagation is used to calculate the gradients of the neural network, right?
Yeah.
And so it is used here, in this algorithm with the neural network. It is used back propagation, so in order to find the minimum, it's still a variational algorithm. It is used the back propagation. My question is, back propagation is used to calculate the gradient in order to reach the minimum in the variational.
Yeah, that's correct. That's correct. So it's a standard deep learning method. But you have the additional methods in order to speed up the convergence, like stochastic reconfiguration, which is often used in standard Monte Carlo methods, which was invented by Sandro Sorella in Trieste. That's a way which speeds up. So when you do this gradient descent, the problem is that you don't deal properly with the second derivative, which is the Hessian matrix. You approximate that in one way or the other. So stochastic reconfiguration is a way to approximate the second derivative of the function we want to optimize. The function we optimize here is the expectation value of the energy. So your gradient is the first derivative of the expectation value of the energy as a function of all the parameters. I will try to show you some of these things if it's a little bit unclear for people. But this is another benchmark case which was run by Giuseppe Carleo, and some of you may also know Alessandro Lovato and Jane Kim and other people. I was not on that paper, but I'm just citing it. So this is a calculation of the electron gas, which is also one of these kind of benchmark calculations in many-body physics. And I know that, how many are doing condensed matter physics here? Yeah, so then the electron gas is something you have in your brains, right? Okay. So,
Absolutely transparent.
yeah.
It's bomb.
So what I wanted to show now, I'm going to take away some of the words here, but I wanted to say a little bit about generative modeling. And so generative model means that you can have labeled data, but you can also have unlabeled data. And generative models are the models which are behind, let's say, ChatGPT or many of these softwares like DAL-E. I guess somebody of you have been using that one. And then you will train on tons of data. And with that, you produce a probability distribution. So if you're familiar with Bayesian calculus, this is one of the basic elements which are used to obtain a probability distribution. And then when you have this probability distribution, you can generate, let's say, new horses, or whatever you want to generate, right? So when you use DAL-E for some of the software, you type in a prompt, make me a unicorn, a yellow unicorn, right? And then it does that for you. And you get some kind of representation. And these models have become better and better, because just a few years ago, you would get humans with 3 hands and 10 fingers. And now, as the models are more powerful, actually you're using much more electricity and so on. These models have gotten better and better. Any questions so far? So this is, yeah.
The last slide where you were talking about optimization.
Yeah.
Probably gradient descent. And is that optimization of the cost function in neural networks, or in this case, since you were talking about some atoms, almost 40 atoms. And you mentioned it's first derivative, so gradient descent. So it's the energy of all that atoms.
So it's the expectation value of the energy, expressed as an integral, and your integral has now a trial wave function with parameters. And the parameters here are the weights and the biases of the neural network.
Yes, definitely.
Yeah. So this is what you train, and then you optimize the energy. So this is exactly the same way you do aberrational multi-color calculation. So aberrational multi-color calculation, you have the wave function squared as your trial probability. So here, a neural network squared is your trial wave function, your trial probability. If you're interested, I can give you you guys codes and everything if you're interested to play around with these things. I'm going to skip some of these slides. And then if you look at discriminative models, the discriminative models are the standard ones, which many of us have used. And that could be a typical neural network, or it could be a convolutional neural network for images. And I have 3 E's here, huh? That's a typo there. But then you would typically train on, let's say, Van Gogh images, or pictures, paintings actually, Van Gogh paintings. And then you would train a neural network so that you can discriminate between new paintings, which we've not included in training, and that can tell you whether this is a Van Gogh or not. So that's a standard discriminative approach. Now, a discriminative model can also give you a probability distribution. So the thing you train doesn't need to be just a plain classification problem like this, but you can actually train a probability for a function which is a probability distribution which discriminates between different cases. But you can also, if you now look at these generative models, there are many of them. And the models which have become extremely popular now are so-called diffusion models, stable diffusion. And they are some of those models which actually used to generate new images and have become extremely popular. And these are models which strike a good balance between tractability and flexibility. And as you see, it's based on diffusion. And I will try to, if we get there, I will try to explain you the difference between some of these models which you have. There are also models which are called variational autoencoders, What you can, if you, is anyone here familiar with variational auto? Okay, okay. Okay. Have you heard about Boltzmann machines or energy-based models? Okay. So these are all ways of approximating the probability. So when it says density here, that is your probability. And you want the probability. You want to train a probability so that you can use that to generate new data. And there are many ways of doing that. So you can start with an explicit expression for it, and then you do an approximation. And you can see here there are many, many different ways of doing that. And some of you may have heard of generative adversarial networks, where you actually extract the probability implicitly. But then you have an explicit treatment of it. And what you will see then, when we look at the explicit methods, is that this is a field where there's a lot of similarity with what we are familiar with from statistical mechanics. So I will try to make those links so that you see the kind of similarities. And you will also see that there are methods from statistical mechanics simulations, which are actually being used to deal with an approximate expression for the probability distribution. I don't know how familiar you are with research in statistical mechanics, but in statistical mechanics there was a popular method which was called the histogram method. I don't know if everybody's heard of that. So that was a method where you, if you simulate, let's say, the Boltzmann distribution at a given temperature, then the distribution of energies is something which can look like a broad distribution with a peak around the expected value of the energy. And then what you could assume then is that at a temperature which was slightly higher, this distribution looks the same. So you could extrapolate from that distribution to another one. So you just generate a distribution which is a histogram over energies. And then you use the one at a given temperature to make an extrapolation to a slightly higher or lower temperature. And this method has actually been used in these techniques as well. That's pretty neat. So there's a lot of physics methods, and some of the optimization part, you will recognize things like Langevin optimization. I guess everybody has heard of Langevin, the Langevin equation. There's Fokker-Planck optimization, all these kind of things which we are familiar with from statistical mechanics and fluid mechanics and many other physics concepts. So I'm putting on this arrogant physicist hat. I'm not claiming that we have invented everything in machine learning. But there is a small thing I wanted to say. Going back to these results which you see here. I think that for us physicists, it's easier to extract something meaningful from a neural network calculation than it is when you train a large language model. So when you optimize with a neural network, you can have millions of parameters. And so your wave function then is just represented by the parameters of the neural network. And we are normally trained to think in terms of simpler pictures. Like when you do Hartree-Fock, we know what Hartree-Fock is. That is, if you think of you diagonalizing a Hamiltonian matrix, it's just a unitary transformation where you transform away one particle, one over its additions, period. So we have a simple mathematical way of understanding what many of these methods we have used mean. So that means that when you train a neural network, you can compare that to traditional methods. And then when you take the overlap between the wave functions or you calculate all the expectation values, hopefully that can say you a little bit more about what kind of correlations are involved. So my claim, and I have no, I would say, more profound kind of insights, is that I think for many of the natural science problems, it's easier to analyze and to extract something meaningful about the laws of motion from deep learning methods. When you train a large language models, you have billions of parameters. I think the parameters now in this ChatGPT, they are 10 to the 23, 10 to the 24 number of parameters which are trained. Okay. So this is just a kind of personal statement. And if you're interested, there are...
Can you give an example of getting something meaningful or training a network? That's two different things.
So you could say when you train the network gives you, let's say, the optimal energy. And then you get a wave function which is represented by the parameters of the network. But since you have all these other methods where you know what they mean, like when you do Hockey-Fock, you have a mathematical understanding of what it means. When you do many-body perturbation theory, you know that. You can use other methods like copper cluster theory, and then you also know what it means. And then you can take the overlap between the wave functions, because when you sum, let's say, a specific type of correlations to infinite order, you know exactly what you can plug in when it comes to physics, physical processes. So it's this kind of analysis, the cost analysis, which then can allow us as physicists to extract perhaps a little bit more. And when you do this physics-informed machine learning, what becomes important then are actually the boundary conditions. So when you solve differential equations, the physics is, besides the laws of motion you have in the equations, is given by the boundary conditions. That's where you plug in the physics of the system. And that can be used to aid the solution of a neural network, where you plug in properly the boundary conditions. And that is that's a very active field, where many people who, in the earlier days, did finite element methods or finite difference, they're actually using this physics-informed machine learning. Where what you optimize is a function where essentially you take the difference between the left-hand side and the right-hand side of your differential equation, and you add to it the boundary conditions with parameters in front of it. And that is your optimization problem. Any more questions? I'm too slow, too fast, too boring. So please just let, I will send to Isaac the slide, and Pino has the slides as well. And if you're interested, then you have a list of many references if you want to read more. And some of these are actually some pedagogical ones as well. The introduction by Kingma. Actually, Kingma is a very young person and invented variational autoencoders, which is a very popular generative method, which is based on applications of Bayes' theorem. But Kingma invented also an optimization method for the gradients, which is called ADAM. And I think I mentioned that one. That has now has 100. Last year when I was here, it had 150,000 citations. Now it has 180,000 citations. So roughly 30,000 per year. It is something like 35 something. So if I'd been Kingma, I would just have retired. When you have invented variational autoencoders and other, what else? Actually, that last paper, if you want to read more, it's very nice. So maybe I should move on a little bit faster because so the typical problem you have is a data set. You have a function you want to fit. If you're dealing with a regression problem, that can be just a plain function of some variables, the input variables, or it could be a likelihood function with x given some parameters. So this bar means x, the probability of x given alpha. And then you have a function which we typically call the risk, loss, or whatever function. And this is the function you would typically optimize, this one. And then you seek to minimize it. And that's where at the heart of all these methods, you have an optimization problem. And as I said last year, this is a place where you can actually make many new friends. And I'm not saying that you don't have friends, but these will be friends which cite you. And this method called ADAM, which is a way to deal with a gradient descent, it has close to 200,000 citations. And in many of, so for many of you are familiar with standard linear regression, because I can skip some of the slides. Right? Is linear regression okay? I can just skip it. But I just wanted to say that when you do that, it's a linear regression because you have these unknown parameters. This matrix contains your input data, and this is your model. And then what you do then is that you take this function here, which is your cost function, which is now written in terms of a vector matrix notation. And then you take the derivative with respect to theta, and you want to optimize it. And linear regression, as you know from basic textbooks, it means that when you take these derivatives, you have a matrix inversion problem, period. So you can think of, you would ask yourself, why is this called machine learning? Because it's just plain linear algebra. But you can think of this as a low-level machine learning. And the learning, when you learn the parameter theta, the optimal ones, is through that recipe. So everything is well specified by linear algebra. But this is the learning takes place through that equation which you see the last one. So you can say we learn. But it's also included in all textbooks on machine learning because you can derive the same thing assuming that that variable y, which is your output, which you measure, so you can make a measurement where you have input x and output y. That y follows a Gaussian distribution. If you do that assumption, you will get the same equations when you optimize. But then you're optimizing a probability. And you find the probability which has the largest likelihood. So this is called normally the maximum likelihood estimation, which you will find in textbooks and statistics. And you also, one fundamental assumption as well, in most of these methods, is that all the variables, like these y's, they are independent and identically distributed. That's a very important assumption. It may not be true, but that is often the basic assumption when you maximize the probability. This is like us doing non-interacting problems. So if you take a harmonic oscillator and you have many particles and they don't interact, the wave function is just a product of the single particle wave functions. And then you square it, and that's your probability. So a very important assumption is that there is no essential correlation between the y's. I'm going to skip some of these slides here. I think I mentioned this last time, is that if you want to teach yourself about many of these central methods, there is an excellent paper by Pankaj Mehta. And the nice thing here is that every result has a Jupyter notebook. So you can actually download the Jupyter notebooks and reproduce everything and run it on your own laptops. So that's a pretty powerful, I'd say this is a very good paper. And then there's also this paper by Giuseppe Carleo. The problem with this field is that it's moving so fast that sometimes you have a feeling that you're not able to catch up. There's so many things which, but it means that there's a lot of nice innovations and new ideas popping up continuously. Do you want me? So one thing I could do is to say a little bit about the basics of neural networks. Should I do? Is that okay? And then we take a break.
Yes.
Or because I think Isaac put up 2 hours.
Yeah.
But I don't want to abuse on your time, guys. Right? Because I know that many of you are familiar with neural networks, but I could say a little bit about it. That is okay. So let me just move on a little bit here. So and let me try to guide you. So a neural network is a way to train a specific model. So the neural network is now your model. So when I did linear regression, you could think of you fitting a polynomial. So you have some data, and you say now I fit a fifth order polynomial to my data. And then these parameters theta we discussed would be the parameters of a polynomial expansion. And that is your fit. And then you can use the Weierstrass theorem and you say something about the error you do in a polynomial fit to the data. Now your model is a network, a neural network. That's something that changes now. So when you do typical linear regression, you would assume a specific model for your data. Now, the network is the model. So you have a number of hidden layers, a number of nodes in the hidden layers, and you also have functions which tell you whether the output from every node should be 0 or 1, or some other value. And then you have a final output layer, which is often tuned to the type of data you're studying. So if you're dealing with a classification problem, yes, no, then you would typically end up with a probability which looks like a sigmoid function. Because then you have two probabilities, 0 and 1. You sum them up, let's sum up to 1, and you have a very simple function. And then this would just make up your model. So everything we do has some type of model. So the architecture of the network is the model here. Whereas when we did a linear regression, you could make a, let's say, a polynomial fit to your data.
But this means that each network has a different hardware.
Yes, yes. Yes, it is. So you could now think of a typical network here. So the first one which you see here is a so-called perceptron model. And you can show, I'm not going to show that, but you can show it. That can be used to fit a linear function. So if your data is like a times x plus b, a and b are parameters, then the first one can actually be used to fit that. And then you would have some input data, the x's. These are weighted by some parameters w. So if you just have a linear function, which is given by a times x plus b, then you can think of a as this parameter w. And then what is normally called the bias would be your interest in the net. So, and then you have a function f, which then models the data in one way or the other. And this is something you do. And at the end, you have to keep, find a balance between tractability and flexibility. So when you're calculating these things, you end up taking derivatives because you're optimized. And when you calculate derivatives, and you're doing this for huge network, then you want to have this to run fast. And normally you want to have analytical functions with nice, simple derivatives. So again, tractability, flexibility plays a very important role. So a standard neural network contains then an architecture, which is your model, with different hidden layers. So the universal approximation theorem, which is an important theorem, let me just bring that up here. I'm going to skip some of these things here. So what a universal feed-forward neural network says in words, this approximation theorem says that you can, with a neural network with one hidden layer, you can actually approximate a continuous multidimensional function, a nonlinear continuous multidimensional function. And assuming then that these activation functions for hidden layers, non-constant, bounded, and monotonically increasing. And I'd say that when Sibenko and Fornik in 89 and 90 in the previous millennium, I like to say millennium because that sounds like 99 years ago. And in machine learning, 2010 is what you would call archaeological times, because the field is moving very fast. But they actually proved that you can approximate such a function. So what it says, if you look down here, so the network, which now is given by the little f, with some input parameters x and some parameters theta, that can approximate the function which you assume exists. So we assume that there exists a continuous function which represents your data. And that function can then be approximated to a given error. So how big that error is something you have to figure out by trial and error. And then this theorem doesn't say anything about how many hidden nodes you need, how many hidden layers. It says that you can approximate such a function with one hidden layer. But when you practice, you will see that the error can be pretty large. And this is what you need to play around. So there's a lot of fiddling around here. So, and then you have the Sybenko, who actually did this, or Nahornik extended this to any non-constant bounded activation function, which could be included. So Sybenko did it for the sigmoid type of function, and Hornik extended it to any non-constant bounded activation function. And then you can show that you can approximate this to a given error. What that error epsilon is, we don't know. This is the same as you would have the same situation if you do Fourier series. Then you know that there is an approximation error. But how big that is depends on how many terms you have in your Fourier expansion. And this is something you have to play around with after when you practice. But this is a very important theorem because it moved neural networks from some kind of black box magic to a more rigorous mathematical setting. But then you have all the practicing. So none of these proofs give you any insights about the number of hidden layers and nodes, nor the magnitudes. So W are the weights which you would have when you link one layer to the next one. And B is a so-called bias parameter or offset. And if you just have this single perceptron, you can think of this as the intercept for a straight line, if you're fitting that. But these become parameters, and you can have millions of them, really millions of parameters, depending on how deep your layer is. So you can, it doesn't mean that the network can be used to exactly compute any function. It actually, you get an approximation that is as good as we want. And then you can play around with more parameters, so-called hyperparameters, and do a lot of tuning and fixing. But the basic layout of a network is the one which I said. So I just wanted to say something. Yeah, Lisa?
There is a way, so if you fix the error, say, I want this network to get me the result of this error, can you get an idea? So there is a way of, say, how many layers or nodes I need to work if I want this error. There's a simple way, or you have to...
No, you have to play around. There is no a priori way of finding that. I know that we have many nuclear physicists here, and one of the first examples these neural networks were applied to was the fitting of mass models for nuclei. I don't know if you remember back from when you took a course on nuclear physics, you have this liquid drop model, which has a lot of phenomenology, and it's actually the polynomial fit of the energy of a nucleus as a function of the number of protons and neutrons. And there is a paper, a very recent one, this is actually from this year, and which now tries to use a little bit more modified application of neural networks. So take a look at that, it's pretty nice. And in my own lecture notes, you will find the nuclear energies and data sets, and if you want to run it, you can run that Jupyter notebook and play around with a simple parameterization. So since we are on Teams now, I actually wanted to show a run with a Jupyter notebook, but I'm going to skip it, since it would be a little bit more difficult to go through that. I thought of just showing a simple example of how you can think of a neural network and the basic algorithm. So this is just a neural network with no hidden layer. And we have a function, which is actually a linear function. And with a linear function, B would be the intercept. But when you translate this into a neural network language, this would be the so-called bias, which is a parameter you fit. And this slope is this parameter W. And the function you want to optimize now is the one you see down here. And you have only two parameters. And there is an algorithm which plays a central role, which is called the backpropagation algorithm. So it sounds fancy, but it's actually high school mathematics. And it's called the chain rule. So I sound like very arrogant now, but actually the backpropagation algorithm is a repeated application of the chain rule, where you then get the gradients. So this is demystification number one. So this is what you want to optimize. So you want to optimize that function C with respect to those two parameters. These are the gradients you want to optimize. And then the simplest way of doing that is a gradient descent. Is everybody familiar with a gradient descent? And then you see now that when you calculate these derivatives, this is just a repeated application of the chain rule. Nothing but that. There is actually, and so I'm just putting up this for the sake of completeness and actually put in a code here. You can move on now to a model here which has one hidden layer, and then you would get more parameters. So you have 4 parameters in that case. And this means that you would have, so this is still just some data x which comes in. And then you have some function here which we call for sigma 1. And then you have a new one, sigma 2, and that gives you an output y tilde. Yeah. So for those of you online, hopefully you can see that. So this is a graph which you don't have in the slides. And to each one of these, there is an input. So this input here feeds in, and it has a variable c, which is given by w1. And then there is some input x plus some v1. And then you have a new variable here, c2. And then you produce a sigma 1 of z1. And that is your output, a1. And this produces an output, sigma 2 of z2, which is a2, which is your model y tilde. And this is something you want to compare with the data you want to reproduce. So the function we want to optimize now is simply a function which looks like this. And you have a factor of a half, because when you take the derivative, you get rid of the factor of 2. It's just, you can decide, define this function as you want. And this is what you have down there. So this parameter a2 is actually the output of the model. And you have 4 parameters. Then the equation gets a little bit more complicated. But this is essentially just the application of the chain rule, as you see. Now, there's something I don't want to talk about, but this application of the chain rule, which we call the reverse mode. So you actually, as you can see here, you start from here and you move back. If you look at this sequence of derivatives here, so you start with the last variables and you move to the inner ones, which are those which you have here. Okay? And you see the application of the chain rule here. When I try to say in a very arrogant way that the training is done by basically the chain rule, which we learn in high school, I did. Probably you guys did it in kindergarten. But the thing now is that there is a very important mathematical project. Have you guys heard about automatic differentiation? So it's a project which was started back in the 70s and 80s. And it has actually been, how to say, not so much in the forefront, but it's simply essential. And some of you may have used libraries like JAX. Does anyone use that? Now, so JAX is based on automatic differentiation, where you calculate derivatives to numerical precision using simple mathematical operations, using the chain. So you can automatize this also to functions and programs. But the thing is that this process which you see here can be automatized so that you with a lot of, because here you need the derivatives of these functions simply. So you can obviously do this by hand, but when the network becomes complicated, this is boring, and it's very easy to make error. So automatic differentiation has 2 modes. One where you move backward, like we did here, and that's called reverse mode. Reverse mode of the chain rule is nothing but the back propagation mode. They are the same. And these are implemented in these libraries for automatic differentiation. And for those of you who use Python, it's JAX, which is the standard library now. That has also just-in-time compilation, vectorization, parallelization, etc. It's a very powerful Python library. The thing which is nice is that this gives you the flexibility to change functions, change activation functions, to change the functions you want to take the derivatives of with no pain. Because normally, so there's a balance you have to strike. Again, tractability and flexibility. So automatic differentiation has a price, which is a number of operations, floating point operations. So sometimes if you have simple activation functions, there will be a trade-off between speed and efficiency. So sometimes it can be more efficient to hard code the derivatives. Because as you can see here, you have the derivatives of these functions. But sometimes it can be more efficient to actually hard code them. But automatic differentiation gives you a lot of more flexibility. It has automatic differentiation has also another mode, which is forward mode. So you start with taking the derivatives here, and you end with a final derivative there. Now, one of the reasons why you do a back propagation is that a neural network can have zillions of inputs, but it may have only a yes or no as output. So if you do a classification problem, you can have data on patients, like 100,000 patients, and you want to classify whether they will get cancer or not, a specific type of cancer. So the output is just one variable. So that means that you can have lots of inputs, but only one output here. That means that the dimensionality here is much smaller than the one there. And that is something which is more beneficial in order to avoid accumulation of numerical errors. So backpropagation is the way to train the network. So you give in, you put these parameters to arbitrary values in the beginning. You get an output, y. You go back propagation. That is one iteration. And then you update all these parameters by gradient descent. When you've done that, you have new values, a new forward step, then new back propagation, and then you keep moving till this function which you have, this c, its derivative, the derivative at the endpoint, doesn't change by more than a quantity you have decided. So if it's 10 to the minus 5, and it reaches that value, you stop. This is the basics of a neural network, the basic ingredient. Any questions? Does it sound too trivial, too difficult? I don't want to go into more the full structure, but you will find that in the slides. But if you have this as just one input, you have the basics. And when you do this, when you program this, you would normally use softwares like JAX, which is a very useful language. So automatic differentiation is a tool. If you haven't used it, you should use it. I actually used that in my PhD because I was calculating derivatives of the order 5. And I realized that what I had published earlier was wrong. And if you use the standard rules for taking derivatives, if you take the second derivative, the approximation, you want the approximation to the second derivative of a function f of d of x is typically f of x plus some delta x plus f of x minus delta x minus 2 times f of x divided by delta x squared. You probably see now. And that is the one which is used in basically all finite difference equations for solving differential equations. Now, if you use that one on e to the x, and you apply this one to higher derivatives, you will just get the wrong results. So fortunately, in my case, in the first papers I published, when I took higher derivatives, the error was on the order of 10 to the minus 4. And I only published results with 2 leading digits. But since then, I started using automatic.
X is not based on this finite difference method.
You should never use it. Numeric automatic differentiation gives you the derivatives in terms of well-known functions. So just keep in mind, there's an important aspect. You can do it on programs, but these functions are no more given by simple mathematical functions like exponentials, sines, cosine, logs, etc. So it's just a repeated application of the same. And it allows you to calculate these derivatives from numerical perspective. Just
improve.
say it.
But to improve with respect to different, you need to know the function,
Yeah.
the neighborhood of the point, and the great precision, and get very small steps. Because otherwise, can you be out and improve
You mean this formula?
this formula?
Yeah.
Yeah, but if you use another one,
Yeah.
evidently you use also the function close by the point, not only the 2 points, but also the 2 points.
Well, yeah, you can improve upon that.
Because otherwise,
But your problem is that if you make delta x smaller and smaller,
yeah, that is a disaster.
you can lose numerical precision.
Right.
And then you are really on your own. So that's the problem. Because that,
Just does not need to choose delta x. Right? It's exactly on one point.
Yeah.
You don't need any other point around it. It's the chain rule. So when you do the chain rule, you don't do finite differences.
so the automatic differentiation is locked by net difference. It's actually operations on known functions. So I really, if you need high precision derivatives, this is a kind of hidden gem, which many people are not familiar with. And it surprises me. If you need high order derivatives to numerical precision, that's the method we use. Okay. I'm going to skip some of these, but it's again.
I use the full conversion of that, so try to use
Yeah. So for the sake of completeness, I have actually included a lot of material on neural networks, and there's also full object-oriented code in the link here. So when I send you the files here, you can study these things in more detail. But I hope that what you see now is the overarching picture and what enters a neural network calculation. And then there's a lot of the playing around with parameter tuning, etc., which comes in addition. You have the gradient descent methods, and the optimization part is really to me, the mathematically interesting. But if we take is it okay if we take just a quick break?
Just
Yeah.
one question as we have the break. So when you are in front of a problem, and you have to decide which network you're going to use. Okay, apart from the number of layers and whatever, but also the activation function and the cost function, what do you choose? So there is a kind of some rules that say, okay, this is my type of problem, then I have to choose this, and that, or you are completely lost.
So if you're doing a regression problem where you want to fit a function, one thing you know is that the final layer, the output layer, you normally don't have an activation function. That just spits out the data, the result you have. And that is your estimate for the output, y. So you could think of this as a whole set of operations where you're trying to fit, let's say, a polynomial to a given degree. One thing you need to keep in mind is, like when you do linear regression, you give in a model as a polynomial. If you do that with a neural network, the network will try to fit that polynomial. And that will be a wrong usage of a neural network. Because the network should find the optimal polynomial. So just keep that in mind. You can always fit a polynomial. So I could bring in an x here and data y. So my data y could be, let's say, a fifth order polynomial. Then I could make a set of input variables which follow a second order polynomial. Then my network will actually try to fit a second order polynomial or fifth order polynomial, because you're forcing it to have that input data. So a neural network is much more flexible, so you should actually just bring in the x value, the inputs, and let the network find the optimal representation. So that's just some kind of technicality. If you're dealing with the activation functions, the sigmoid has a problem And that was actually one of the things which almost killed the field, because the sigmoid function, when you plot it, and that's why people don't use it so much anymore. So if you plot the sigmoid function from minus x to plus x here, and then you have 0 here and 1 here, it looks something like this, like that. Now, the problem with the sigmoid function is that you will actually have values x, which can be large or small. And then you see that it flattens out. Then the gradients become small. And then you have a vanishing gradient. And that means your training will stop, because the gradients become 0. So if you look back at that equation I had for the simpler case, so here is just a general case if you want to code it. So if you look at here, if this vanish and you're calculating these derivatives iteratively, then the process will stop. So the sigmoid function is a paper by Benjo and Gloro, which came in 2010, where they actually demonstrated that many of the problems with the training of networks had to do with the sigmoid function, which has been used quite a lot because it's inspired by neuroscience. It's easy to understand it. If you could say that if it's below 0.5, you give the value 0. If it's above 0.5, it outputs 1. So it is a very nice function. It is a probability distribution. Has all the features you like to have. It has a simple derivative. It's easy to plug in, etc., etc. But it has a problem with vanishing gradients. And what many people did was actually to simply say, okay, if my gradient vanished, I just put it back to normal value. And then I keep it free, which is not very satisfying. So then people came up with other activation functions. And this becomes a parameter in your model, which you will play around with exactly.
And at the moment, what are the mostly used activations?
So we have this ELO function, an exponential function. There's a real function, which is just a typical function which will be given. There will be something which looks like this, and then it goes up like that. So that's a typical activation function. But that brings in new parameters because it has a slope. How fast it goes here is given by a slope again.
This is the leaky rail.
Leaky rail, exactly. That's the leaky rail. Yeah. And then you have the rail function, which just goes to 0 here. These are also functions which have very simple derivatives and are easy to implement. So it's again tractability and flexibility which comes to play. Because if you make so there's something which is called Bayesian machine learning, where you actually train a network so that every such node has a probability distribution. And that is a little bit more realistic. But then, when you train a probability distribution, that becomes more expensive. So there's always this kind of trade-off, tractability and flexibility. Because when you have millions of parameters, you need something which can run fast.
Suppose you want to calculate the derivative of a function,
Yeah.
that you know point by point, but not everywhere.
Yeah, yeah.
It's possible still to do calculate the derivative.
Oh yeah, but it would be quite expensive. So it's always
a problem.
There's always a trade-off with that, unfortunately. So the thing I wanted to say a little bit about, and maybe we are a little bit shorter after a small break, is to just give you the feeling of how you optimize a generative model. And there's a lot of playing around. So we could take the Boltzmann machines, which have been very popular, and this is what Giuseppe Carneo did for quantum mechanical problems. And gave very nice results for easy model, Heisenberg models, these spin type of models. Should we take a break or just stretch legs a little bit?
Yeah.
Or
Just
yeah, 5-10 minutes. Cos'è? No, no, ma spero che sia la cosa più importante è che la gente c'ha una riflessione di cosa significa questa cosa così. E poi ovviamente uno sì.
Collegamenti.
Comunque lì c'è un sacco di anni, quanto i ragazzi, quelli che sono studiati.
Ma lì dove?
Se tutto questi differenti sulle mie lezioni sono stati vediamo quanto abbiamo sbagliato.
Quindi non c'è un modo a priori di sapere.
No. Diventa una sperimentazione.
Questi io con 7 dati, questo tipo come super value, adesso faccio il mio modello, c'è anche la funzione d'errore. Poi c'è mostrato il giorno della funzione del numero di interazioni, ma come sei sicuro che a un certo punto non sei finito su un minimo locale, per esempio?
Nessuno lo sa.
Perché potrebbe succedere.
Sì.
Che vai a molte interazioni, sembra tutto piatto, all'improvviso, boom,
Ad esempio, fai dei salti, sperando che sia sufficiente.
Uno dei metodi per evitarlo è il stochastic range.
quindi vai provato.
E poi questi calcoli qui spesso li ripeti. E alla fine in realtà c'è un valore atteso per quello che c'è.
Con un errore dovuto anche per questo cambia anche il valore iniziale dei parametri, quindi cambia anche il dato finale, quindi hai una distribuzione come testa.
No, ti dà una certa flessibilità. Io sono rimasto stupito dai risultati che abbiamo ottenuto sul calcolo Maribor, veramente stupito. Non me l'aspettavo, io mi aspettavo.
Ho dimostrato?
Io mi aspettavo un risultato paragonabile con il calcolo variazionale nucleare. Quello che mi aspettavo. Si vede che c'è molta più flessibilità nell'utilizzazione nel cercare un'ottimizzazione della metodiana che c'ha.
Quindi voi avete preso la rete come la funzione d'onda, no?
Sì.
E poi quello che minimizza dei parametri della rete è l'energia
l'energia come funzione
dei parametri della rete.
Perciò se tu c'hai, come nel nostro caso, c'hai diciamo 14 particelle in 3 dimensioni, l'input x è 3 per 14. Questi sono i 3 dati di input. E poi lì se c'hai 100 nodi.
Va bene, ma 3 per 14
alla dimensione x, y e z.
Sì, ma questo sono 14 per 3, sono 12, 72.
Sì, qui sono gli input.
Ma non sono pochi.
No, ma gli input sono decisi dalla tua dimensionalità. Quando tu fai il fit per una funzione d'onda, questo qui ovviamente lo fai e lo fai, però i tuoi dati di limite sono specifici, tu c'hai una posizione.
Sì, la voglio dire, ma vabbè, no, cioè 72 più, cioè la domanda è quanti?
Puoi fare a quanti ne vuoi.
Ma come dipendete, cioè, queste cose, cioè?
Sì, ma sono a caso, le posizioni sono a caso.
Quindi fate nel tempo del random e poi
X, Y e Z, però mi fa
poi
a caso.
No, penso che non potete. Dovevo dirlo per cattiveria.
No,
e quindi questa è la hamiltoniana che interazione.
Ma qui abbiamo una bioness, ma poi adesso stiamo aggiungendo la forza tensionale e tutto quanto, ma qui quel calcolo lì è una bioness. No, la cosa è come dici tu, cioè, tu devi sempre essere scettico. E chi? La scienza è essere al tutto, e poi c'è quello che ci muove. Lo sai,
Tipicamente quanti, il set per questo in questo lavoro, il set di input, quanti punti, cioè quanto è difficile, quanto è grande?
lì tipicamente abbiamo fatto un centinaio di set, un centinaio, un migliaio di set.
Per 72, diciamo.
Sì. Poi c'hai tipicamente il calcolo più massiccio è 5 strati nascosti e con 100 neuroni in ogni strato. E ti dà un sacco di parametri. Quindi c'aveva un milione di parametri ottimizzati. E tu non puoi sviluppare un'intuizione su quello che fai, perché c'è una funzione multidimensionale di ottimizzazione. A un certo punto non è che puoi dire a uno che adesso c'è questo tipo di cooperazione, quando fai l'altro tipo sai esattamente cosa è. Posso andare a partecipare con un buffer, sai anche che tipo di cooperazione c'è. Quando fai un race function, parliamo c'è altri copy cluster. Sai cosa metto dentro. E qui puoi pensare che adesso se tu crei questi risultati, dici questa è la mia funzione ottimizzata, allora puoi prendere questa funzione per la richiede di function e vedere dove si destina.
Una domanda, cioè, la fisica comunque non è nella rete, la fisica è nell'input. Nella rete la
rete è semplicemente un modello, una funzione. Come tu fai il calcolo variazionale unificato, c'è un modello con le correlazioni tipo gesto, ci metti dentro un determinante di Slater e poi ottimizzi il tuo fattore di gesto.
Come si può fare senza un calcolatore standard?
No, questo qui devi farlo su un supercomputer. No, per questo sistema qui non c'è.
Però struttura standard, diciamo.
Sì, totalmente standard. Totalmente. Sì, no, la GPU e CPU. Sì. Poi lì Alessandro ha fatto girare su una macchina che c'è e lì hanno il calcolo qui, non è tanto diverso da un calcolo variazionale multiplicato, di complessità numerica. No, qui abbiamo senza TensorFlow, senza Python, l'unica cosa che aggiorni è CHS. Sì.
Come l'anno 6
Sì. E poi con JAX fai la differenziazione.
Quindi è fatta a mano, quindi ogni layer messaggio di codice implementa codice. Col terzo flow tu metti una reghina dentro di qualcosa e gli fai
Io penso che ogni volta che tu aggiorni il tuo vocabolario, spesso non funziona. Infatti io sto usando Python, ma ci sono due biblioteche, non so se li conosci, una si chiama TensorFlow, che fu rilasciata da Google nel 2015. È una delle biblioteche standard per diciamo, l'apprendimento automatico, che c'ha un regalo difficile. Tu poi fai il calcolo, tu chiami il modello con la rete neurale, con 5 strati nascosti, certo numero di funzioni di attivizzazione, nodi nascosti, bla bla bla, e diventano tutti quanti i parametri che tu dai a questa biblioteca. E poi Facebook ha fatto lo stesso e la biblioteca si chiama Python. E poi c'è anche tante altre biblioteche.
Se è sviluppato da Google per Facebook, perché dice qualcosa l'interesse che c'è dietro.
Sì, no, guarda, è un campo che è sempre esploso. Nel 2015, quando rilasciamo questa biblioteca, quello anche tu devi semplicemente scaricare usarlo. Sì, sì, calcoli abbastanza pesante. Sì.
Devo andare un minuto.
Ci sono i reduci, quelli che ancora, quelli che hanno sopravvissuto. Esatto.
Io l'ho visto uscire
Sì,
veramente con te.
ci sono tutti là.
Quindi tu hai i tuoi ricordi, hai le tue lezioni online sul GitHub.
Sì, vai,
Sì, c'è il tuo sito dove posso
sì,
raggiungere.
sì, sì, sì. Aspetta che adesso, questa è una buona cosa, eh. Adesso vediamo un attimino se c'è ancora qualcuno che vive in rete qua. Aspetta un attimino, se possiamo andare. Aspetta un attimo, adesso lo facciamo. GitHub. Vediamo un attimino dove
Facciamo.
facciamo così e poi scegliamo. Aspetta un attimo, qui c'è quel segno matematico, quello che c'è così, quel segno là, com'è che lo raggiungi sulla tastiera qua? Cosa? Sopra Z? Shift 7, Eccolo, perfetto, ottimo. Ottimo.
Vabbè, se voi sono facile.
Non può avere preferenze.
Oh. For all the survivors, thanks for your patience. So I just want to say one thing. Instead of you looking up these long links, if you use GitHub, you can just go to my GitHub site. So, my username on GitHub is the one you can see here. So if you go to that one, you will find my lectures on machine learning, which is this one. But then there's also the one on advanced one. And if you go to the one on advanced, there is actually on the public folder, everything I showed today on the public folder here, there is one which is called Catania. Catania. And there you find it. You find the PDF file, you find the Jupyter notebook, you can run programs.
So we can also see whenever we are free.
So like a GPS.
I cannot tell my wife. I couldn't find it because I was there. Now, so feel free to use this as you want. If you click on Catania here, let me just increase the font a little bit. This should be Control plus. Yeah. So you can, if you go to the PDF, you will find that PDF we were looking at, Catania PDF. If you go back to the Jupyter notebook, this one, then there's a Jupyter notebook where you can also run the codes. So there are many codes example as well. And feel free to use this material as you want. My basic philosophy is that knowledge should be freely accessible. And this is also something which is, for those who are from this country, there is a beautiful document, which is the closest I get to poetry, which is called La Costituzione Italiana. It's close enough. And there are some statements about access to knowledge, which are written in a beautiful.
It's completely useless in Italy.
When you read it,
Yeah.
when you read it, you feel it. Really. Sorry, this was a paper. Okay.
So I'm sorry having you like this, but it's a really a pity.
No, but the thing we put here with the thing I teach all the materials through level. Use it as you want. As a public employee, this is one of my jobs. Okay, guys. So let's look a little bit on these models. And now I should go back to full screen. And this is Teams. So how do we do that? Yep, there we are. So let's just do one thing, one of these, because else I'm going to ruin the rest of the day. So let's just look at, because to get that philosophy, then you have the basics of generative models. And the Boltzmann machines are very easy and intuitive to understand. So if you get that one, these are called energy-based models, and I will try to explain why. And then variational autoencoders, they add on top of that the Bayes theorem. If you know something about autoencoders, you understand why it's called like that. And then diffusion models are actually variational autoencoders which are stacked on top of each other. And then you set up a Markovian chain in order to train a probability distribution. But let's look at the basics. So these are things we have seen many, many times, okay? And this is actually what Giuseppe Galileo and Michael Troyer did in 2016-17 when they studied the Ising model, the quantum mechanical one. And they applied a neural network to that. And in this case, what you have is probability, which we know is like that. And these are called energy-based models, because we know that when we look at this function here, this, if you think of the Boltzmann distribution, and let me just bring out this blackboard here. If you think of the Boltzmann distribution, you have a P of X, and now I have the Boltzmann distribution will be something like this: E to the minus inverse temperature E, and this E could now depend on X, for instance. There could be a dependence there. Normally, you would just see that E here, and then you have the partition function. So you could think of F like that. Now, this quantity which you see here now contains also some additional information. And this will represent the hidden layers. So a Boltzmann machine in its simplest form is called a restricted Boltzmann machine, and it has a visible layer. So you will just have some input nodes. So if you have two particles in 2 dimensions, then you have 4 input nodes. X and Y for particle 1, and X and Y for particle 2. And then, so this will be the X's here. And then you have the, you can have as many as you want here as the hidden ones. We call this H. And that's why you call this probability as a function of X and H and theta. The theta are additional parameters. And these thetas would be the links between the X's and the H's. So you would have a W here. You could also have a bias here, an A and a B. I'll come back to the type of Boltzmann machines you can have. And now you see the difficulty here because you have the partition function. So all of these generative models, the bottleneck is how do you deal with the normalization cost? That's the bottleneck. So in a sense, I like to, when I teach about generative models, I like to start with these because we as physicists, we are pretty familiar with the kind of problems we face here. And when you take a course in statistical mechanics, we only solve typically a 2-level model. Because then you have 2 states. But here now, there's another technicality which is important to keep track of. So this will be the full probability you want to train, but you're not interested in that. What we want is just P of X. So what you want is what in statistics is called the marginal probability. So the marginal probability will now be P of X, which is a sum or an integral over all the other degrees of freedom. And now I'm skipping this thing. So this is your marginal probability, because at the end, what you want to generate is a probability for X. You're not interested in the hidden layers, because that is an additional parameters which allows you to train a model. And a restricted Boltzmann machine is a Boltzmann machine where you have only one hidden layer. And the reason for that is that it's easier to train. You can stack them with more hidden layers, but that becomes more difficult to train. You also have only connections between hidden and visible nodes. There are no inter-node connections in here. You can have that, but that gives, again, more difficulties in training. So again, tractability, flexibility. So this comes always into play. So this looks impossible. How do we train this, right? How can we get these probabilities of what we want, or these marginal probabilities? So this is essentially what we want. And you also want the probabilities for the H's when you're doing the training here. Because that probability is the one which tells you what value H will have. So in the training, you need both these quantities. And the end product is P of X as a function of the parameters. And then the question is, how do we actually optimize this? So the thing now is that I actually made a change here. So your partition function is a sum over all the variables, as you have in standard statistical mechanics. And you want to optimize this Z as a function of theta. And as you know, if you look at a binary type of problem, like a spin type of problem, if you have the n values for X and n values for H, you see immediately that this just explodes. If m is just 10 and n is 10, it's already a big number. So it becomes quickly intractable. This is a bottleneck, irrespective of any. So all these methods actually dealing with different tricks or ways of handling the normalization constant. And then the assumption which I mentioned before the break of independent and identically distributed variables. So you could now think of your X being the product of all the single X's. And this is a quantity you want to optimize. So you obviously are not interested in the minimal likelihood, you want the maximum. So you want to maximize that. Now, so what you want is actually to maximize this quantity here. And you're thinking of all the X's as independent and identically distributed, so that you have the same probability distribution. Any questions? Statistical mechanics is actually, to me, when I was a student, that was really a fantastic thing, because I started with chemistry the first semester, and we had a chemistry teacher who just gave us all the equations, Helmholtz free energy and so on. And we asked the chemistry teacher, what does Helmholtz free energy mean? It's a formula, use it. And then the second year, we had statistical physics, and we derived it. But for me, statistical mechanics is really my really favorite. Really. It was so frustrating with somebody who just gives you equations, right? Use it. I guess many of you have encountered that situation.
You should not like quantum mechanics.
What, say it again?
So you should not like quantum mechanics.
I actually want to do my thesis in quantum statistical field theory. That's what I want to do. The guy who did that was on sabbatical.
But I was referring the fact that for Neumann postulates are more modestly called the rules.
That's a good point. That's a very good point. But this is the quantity, and you see that if you want to take the derivative of that quantity, that becomes difficult. And if you want to optimize that problem, it's not that easy to take the derivative. So the equivalent problem is taking the log. And that is the trick here, which simplifies and makes the calculations possible. So instead of optimizing the probability itself, you optimize the log. And then you have a log of a product, which is just a sum. And then the final thing you want to calculate is that one. You want to take the derivative, the gradients, for all the parameters. So theta is now, if you have, let's say, 4 visible nodes, and let's say you take 4 here, then you have 4 times 4 values for W, 16 parameters, and then you have the biases, 4 and 4. So you would then in total have 24 parameters for that specific case. So theta would be 24 parameters. So you would have a 24-dimensional problem you want to optimize with gradient descent or any of your favorite methods. Now, the thing is that when you look at that one, there's a trick here. So what you end up with is actually to calculate these quantities. So here, when you evaluate this function f, which can be this function here, or any function you choose, actually there's an interesting, because this method, I'd say, till 2010, many people tried to use Oslo machines for classification of images, but then convolutional neural networks came to the market and just wiped out all the interest for Oslo machines. So in a certain sense, people lost a little bit of interest for these machines. But then what people have done lately, which is very interesting, is just to replace this function you see here with a neural network, or convolutional neural network. So you're just replacing, you can play, and this is the thing which is very interesting with many of these machine learning methods. You can think of a neural network as a function. So that function f, which I have, could be anything, as long as it is a function which is positive, because you need to define a probability. Right? So that's important. That's a constraint you have to think of. So people have actually been using neural networks with high level of success. That has given a new boost to energy-based models, because the interest to me, when I started to look at this some 10 years ago, I thought this is interesting from a pedagogical point of view. And it's also easy to get started. But now it's gotten quite a revival. So here, the first term, you have the function, and x is your data. So you simply evaluate that sum. So that is not an expectation value. Now the trick now is that you don't know the partition value, but you can calculate that as an expectation value, and that is a trick. Because you would think that this is impossible because z, the partition function, is just impossible to calculate. So if you look at that one, as I say here, this is the most problematic term. Both x and h can be huge degrees of freedom. And the derivative of the partition function is actually rewritten in terms of an expectation value. And when it's an expectation value, you can use Monte Carlo Markov chain and calculate to a given precision, like you evaluate an integral to a given precision. And that's where you do Monte Carlo sampling. And the way people do that is not metropolis sampling, because that is often more expensive, but they use Gibbs sampling, where you actually calculate what's called the conditional probability using Bayes' theorem. And then you just re-evaluate everything again and again. If you go into my lecture notes, you will find examples of how to implement the Gibbs sampling. That is a very efficient way of generating the probabilities. Now, for many of these modern applications, even Gibbs sampling is less efficient, and that's where you have something which is called non-event sampling, another physics application. It's actually quite fun to see how many of these people from computer science and mathematics are rediscovering many of these basic physics equations and baking them into machine learning methods. So what you do then, if you look at, this is essentially what we do when we teach statistical mechanics, right? when you're calculating Helmholtz free energy, this is the quantity you would typically calculate. So we know that the derivative here is just this quantity log is this one divided by this one. And then you can write this out in more detail like that. So you have summing over the x's like this. And then you can rewrite this function. And this is the important assumption, is that it is larger or equal than 0. Because then you can rewrite f as exponential of log f. And then you can rewrite this one as something which is going to look like an expectation value pretty soon. So what you get then, when you write it out, this is your f divided with that one, which is your probability distribution. And then you have the derivative of this function, which you have fixed. This is your model. So you have a model for f. And that is what you need to plug in. So you have to decide on a model for it. This is done in every one of these generative models. So when you go to variational autoencoders, where you play around with Bayes' theorem, you use normally as a conditional probability a Gaussian. That simplifies the mathematics of it. In the fusion model, it's actually stacked variational autoencoders where you actually have products of Gaussians. And you can calculate this analytically. Again, flexibility, practicability. So you need to decide on a model which is relevant for your case. And this one is nothing but an expectation value where you draw points according to the probability distribution you have at a given level of training. So when you're going back and forth here, you have new updates of the parameters. You get a new probability distribution. So this f divided by z is just your probability distribution. And this is the quantity then you use to generate the new points at every level of training where you have updates of these parameters. And then you have the gradient here, which you use in a gradient descent approximation. And this one, you know that when you calculate a quantity like this with the Monte Carlo methods, so let me just pull up this one here. Then I'm going to stop pretty soon here. So when you calculate an expected value, this is just the sum over the xi's, and then you have the p, this is your probability, and then times x of I. This is pretty familiar. Now the thing, you know that this one is normally approximated with a sample mean in this specific case. So you have the xi's, I should write I here, and then an x of I. So you replace that one with a uniform distribution, and then you invoke the Nully's law of large numbers, and you hope for the best. And that is why in Monte Carlo calculations, they're just data greedy. The more, the happier we are. So this is a typical way you would approximate that. That means that here, you just have a sum over all the samples you pick. And that constitutes your representation of the derivative. So what you get then, when you calculate this, is this formula here, where you use your data, x, and here you generate new x's with the probability you have at this level of training. And this goes on till these gradients vanish. That's the basic recipe for a Boltzmann machine. So when you deal with variational autoencoder, it's a variant of this, but it's a little bit more complicated. But if you get the basic philosophy, this is the basic philosophy of a generative model. And if you take the Boltzmann machines, a typical expression for this function is f would be something like this. And where a, b, and w are parameters you train. So if you have a binary case, which is what Carleo did when they had this paper in Science in 2017, and they looked at the Ising model, then X takes only values like 0 and 1. And H takes values like 0 and 1. And that could be a spin system. Spin up, spin down, a binary case. This is essentially what they did, because also when you plug in that function, what you do now is that you have you can write it out in a more compact way like this. So it's a, these are all scalars, obviously, they have to be. And then you simply take the derivatives of that function. So some of the derivatives you need are very easy to set up. So this is a case where you can set up all the parameters for training in terms of analytical function. And that is one of the reasons why Boltzmann machines were so popular. But you see very quickly that they are less flexible. If you have a continuous variable, you have to guess on a type of expression for the energies which reflect a continuous variable. So in a sense, it's simple, it's easy to train, it's easy to set up. You will find a simple code which I have for training a binary machine, but you can make them a little bit more difficult. So binary is what was used for this kind of spin systems. If you're, suppose you're dealing with a harmonic oscillator, you could think of something like that, and that would give you a Gaussian binary. If H takes binary sets of values, and then X would be a continuous value. So the way people have used this in quantum mechanical studies is to take, if we go back a little bit, this quantity which you see here as your wave function square. And then instead of, so when you do a quantum mechanical calculation, you're not doing, so the quantum mechanical calculation is easier. Because in a quantum mechanical calculation, you don't need to do this, because you optimize the energy. So you have a model for your wave function, which is given by a probability, but instead of taking the derivative of the probability, and that is your optimization problem, you take the derivative of the energy as a function of parameter. And that gives you a much simpler function to optimize. And this is essentially what people did when they applied Boltzmann machines to quantum mechanical problems. But you see quickly that the problem here is that, so if you have this Gaussian binary or Gaussian, you can still get analytical expressions for everything you want to take the derivative of, everything which enters your calculations. But if you have something more complex, this becomes much heavier to train. And then you need to take numerical derivatives, etc. And then again, you have this flexibility versus tractability. Here it's flexible to a certain sense, a certain limit, and then it becomes less flexible if you have a more complicated problem. And that is why variational autoencoders and diffusion models are much, much more popular than Boltzmann machines. They are less flexible. So it's always this kind of balance you have to strike between flexibility and tractability, always. Now, there's a lot of more information. There's a simple code here. I have links to many other type of problems. If you're interested, there are. So you may know that there are libraries. So I like to use PyTorch, and that is simply because I run things on a Mac, and every time I update things, TensorFlow doesn't work anymore, and then I have to reset things here.
Yeah, included in TensorFlow.
Yes, and PyTorch.
And also PyTorch.
It is. I like to write things from scratch, but sometimes PyTorch is very flexible. TensorFlow is also a great. You know the story about TensorFlow and PyTorch? So in 2015, Google released its machine learning library, which is TensorFlow, and Facebook did the same, which is PyTorch. So these are libraries which have been developed by the staff of these two big companies. And they're very flexible. They allow you to study tons of things. There are quantum mechanical variants of them, etc., etc. They're just huge libraries. There's a huge community developing them. It's open source. No, I don't think it's open source. Yeah, it's open source. Yeah. Yeah. I think it's developed. I'm not sure. So in the slides here, there's also I put in a lot of information about the variational autoencoders and so on, but I think I should stop here because I don't want to abuse too much of time. I wanted to give you the kind of basics of generative models and where the bottlenecks are. And then you have lots of refinements. So if we go back to the very beginning, I have this taxonomy of methods. These are some of the most studied methods nowadays, and diffusion models are extremely versatile. Autoregressive models are very much used in these large language models. They are based on the entry point is a recurrent neural network. We have things I didn't mention anything about, normalizing flow models. Generative adversarial networks also very much used. But it seems now to be quite some momentum in the direction of variational autoencoders and diffusion models. And for us as physicists, I think like the problems which you guys, Dino, Luigi, Trey, and many others have been dealing with here, I think looking at diffusion models and variational autoencoders to train in an unsupervised way could be very interesting. And there was a recent physical review lecture now, which I think I sent an email to you guys, which does exactly what I think you need. Okay, guys. Thanks for coming. Thanks for being so patient. Questions? Things you're wondering about?
You have to teach to some young physics students a programming language.
Yeah.
Which programming language?
So the I guess you guys in Catania, you start with Python, right? Don't you? The basic programming course.
Once it was in C++.
I see.
Now we turned into Matlab or Python.
Okay.
That's changed.
Now, I think I would recommend having the first programming course in Python because many of these libraries have a Python interface. So you will often see that the inner core is a C++ program, but yes. I grew up with Fortran. I have so many dusty Fortran decks that the Fortran object-oriented Fortran is nice. But I kind of tell students, used to use Fortran because they will look at me. I'm an old guy, but then they will think, well, who's this Methuselah you're talking to me? And also Python is extremely flexible. And with JAX, it's really getting up to speed. It's really getting up. And with age, you also get lazier. And C++ is a very complex language. It's a very rich language. And sometimes I just get lost in it.
But just a comment, I really would love to study. It's pretty nice. It's even a different perspective also.
Yeah. That's why I like these generative models. Because, and I think we as physicists, we actually want everything. We want predictions, correlations, causations, and error quantification. That's why I like generative models. And I think they have a lot of things which can be interesting for us as physicists, both for unsupervised and supervised. In that paper I sent to Luigi here, is actually doing a training of phase transitions with unsupervised data. I'm actually going to look at that later. I think it's very interesting.
It says that the reason is that probably I put it on a. It's even more technical than it appears. Think to a quantum phase transition.
Yeah.
And they want to recognize the finite temperature quantum critical phase. So what is in the middle, and it is nothing or nowhere. Is it how can you assess? I mean, is it so? I mean, it should be so powerful to look at this and how. I mean, that are there attempts in this direction? Because let's say when you, I'm interested in problems of urban systems.
Yeah, yeah.
Large systems coupled to large environments, and it's a situation in which there is no black and white. It's everything is gray, and you have to recognize some global property, even to guess what, which is not an order parameter. I would say.
So, what I can say, so this is not things I have done research on, but there are actually quite many people who have used deep learning on classification of phase transitions and extractions of order parameters.
Yeah, but when you have crossovers, this is the point.
Yeah, I have never looked at that, but I know that people like again Carleo, who is a kind of wizard nowadays, has studied that, and then you also have. I know some other people. I could send you guys some references of things. There is actually another Italian in Swansea, Luigi Biagini. All these Italians are probably. And he has done a lot of. He's a statistical physicist, and he has applied many of these methods on.
That's there were people that it was a people of science, and we gave those poets, scientists, also not scientists.
So also my own take on many of these problems is that we all struggle with the explosion of dimensionalities and degrees of freedom. So I see this as a way to find some efficient representations of the degrees of freedom which are relevant for systems. So hopefully we can learn, and I think we can actually extract some physics from many of these deep learning methods. But I think what you guys are interested in is something which is very, very, there are people who are doing this, but I haven't touched it. So I spent most of the time on solving Schrödinger's equation.
In fact, I can ask to other questions. First, for sure it has been done, but we use photophisics model in which you have to recognize something. What about clustering stars?
I don't know.
I mean,
I don't know.
is it
I
very
know,
easy to it should be
yeah.
somehow intriguing
Yeah.
to
What I know is that, like in Trento, Sandro Stringari's people, there were people actually looking at some of these things.
should be should,
Yeah.
should be also connected to.
Yeah.
And the other thing is I my mind was a rehearsal that you are interested in log mode. Is there something, of course, that should, is there something like replica trick or Magnus's function in this business?
I don't know.
We also both want to take that shot. And then it works pretty.
Going back to the phase transition.
Yeah.
The machine can understand if the system is below or above, and probably up. I suppose you simulate the system. It's possible. It's also possible to see where the phase transition is by correlation rate. What is the advantage to doing the other way?
I think the thing they did was mainly to see if they could recover what has been done.
Okay.
That's my feeling of what people did.
Other questions?
Yeah. So one of the papers we can actually, since we have a web browser open here, there's a paper by this guy, Melko, Nature Physics. So that says a little bit about nature physics. No, mature physics.
That's I think that the problem is meaningful because
Yeah.
you think to a physical system and to a measurement.
Yeah.
Why should I look at a single configuration? I arrive always in time. I can measure average. But think to, I don't know, kind of keep on Zurich
Yeah.
problem with the universe. Do you have many samples of the universe now?
So one of the first papers was actually this, let me just increase the fonts a little bit. So this one by Juan Carrasquilla and Roger Melko. This is one of the papers, one of the first ones actually, where what they did was what I said about feeding in images of the spin configurations and then being able, but they also say that I think some of them also extracted the order parameters. Yeah, yeah. I haven't done any research yet, so I have a very superficial knowledge of what they've been doing.
I think I read many other things.
Yeah.
Just nice question. In this unsupervised method,
Yeah.
what do you know? What do you copy? What is the cost error? I mean, if you know the output, how you compute the?
Oh.
So how you define the error in that case?
So in this specific case, I mean, no, what you get in these methods, you can calculate the if you're thinking of the errors, you can find the errors on the parameters by calculating because you have a probability distribution in terms of the parameters. So you can is that what you're thinking of, Isaac? When you say the error?
Well, the cost function. Also, what is in the case of this unsupervised method?
Yeah.
Because for the supervised, I mean, I can understand. You have the output and the prediction from your network, and then you minimize this cost. But in this case of the unsupervised, what is the equivalent?
So in a quantum mechanical case, where you don't optimize the probability itself, you optimize the energy. So you're repeating the variational multi-color calculation, but with a Boltzmann distribution. And that gives you less flexibility because you have this Gaussian binary. For the spin system, which they opted for in this Science article in 2017, then you actually had a Boltzmann machine which did fit for that specific case. Because if you think of the Ising model, and let me now just if we just go down here a little bit. So let me just bring up this binary. If you think of the Ising model, it looks very much like what you have here. So with the nearest neighbors, sigma I, sigma j, and then you can have a sigma j term in addition. So it's the energy function you choose is pretty close to the function itself, but you don't optimize the probability, you optimize the expectation value of the energy with respect to those parameters. So the quantum mechanical case is easier because you don't need to look at the partition function. And I'd say that paper by Carleo and company, that really sparked the interest here. So if you look at, so let's just take, you can take that one. If you're not familiar with that paper, and this is a paper which can be easily reproduced. Now, so it's this paper here, and that's published in Science. So this is the paper, and you see the number of citations here. It's pretty good. Carleo has also tons of lectures and with quotes. And they've developed a very nice libraries for machine learning and also quantum computing, which is called NetCat. That's Carleo's library here, actually. So you can, let me bring that one up. So it's netcat GitHub. Highly recommended. Open source. Has many Hamiltonian spectra. And let's say this is what really kicked the quantum mechanical applications. So this is my more narrow niche where I live. Feel free to ask more questions, or if you want to do something else, I'm not offended. Actually, you should do something else.
And you're going to come back.
Yeah, we had too much. Good time. But I'll open that. That's it. Yeah. That's the rest of the day.
Puoi venire l'anno prossimo un altro mese.
Sì, volentieri.
Devi venire a dicembre, qui l'estate è più, a dicembre l'estate è più.
Ciao Martino, grazie per il seminario, è stato molto interessante.
È stato un piacere vederti.
Spero di vederti.
Saluto tua moglie, grazie per ieri.
Ciao.
Ciao. Sì, mancano le tappine, queste riunioni qui tornate.
Cielo, si chiede di un passaggio di nome? Adesso metto via tutte le mie.
Parliamo di intelligenza artificiale e generativa. Genera immagini.
Adesso, con i metodi generativi, in realtà c'era questo campo nell'apprendimento automatico del calcolo bayesiano, ed è quello che ha influenzato molto questi tipi di metodi, che in realtà utilizzi il teorema di Bayes per sviluppare i metodi. No, per esempio tutti questi modelli per la generazione di immagini è basata su due candeli, una probabilità, e poi questo ne riutilizzi per mescolare. Sì. Poi diciamo l'ottimizzazione la fai su queste macchine che questa è la Google in Norvegia, che usa il 5% della produzione elettrica nazionale. Ve l'ho raccontata questa storia qui, no? Sì, vabbè. È stato questo comune che... Sì.
Questo si spegne in qualche modo? Come si va a spegnere questo?